This recording will be the Chapter 3 notes in first year chemistry over scientific measurement. The first thing that we do in class is we distinguish between the terms qualitative measurements and quantitative measurements. Very simply, a qualitative measurement doesn't contain a number, so it is just an adjective describing an object, such as something that's short or heavy or long, or let's say a room that's cold. A quantitative measurement actually has a number for the value of the object. So if a person is short, they might be 4 feet 6 inches tall. If a person is heavy, they might weigh 600 pounds. If an object is long, it might be 22 meters long. And if the temperature outside is 5 degrees Celsius, you might classify it as cold. The next thing that we do is we distinguish between the terms accuracy and precision. And accuracy is how close a single measurement is to the accepted value, or whatever the right answer is supposed to be of what you're measuring. If you have a group of measurements and you want to see if the group of measurements is accurate, you're going to have to find the average of that group of measurements. But anyway, you're comparing the average of the group of measurements, or a single measurement, to what the accepted value is of what you're trying to measure. Precision, on the other hand, is how close several measurements are to each other. And this can be best explained by the targets which are on the next page. So if you had to describe whether these shots at a target, and you're obviously trying to shoot at the bullseye, if these shots are accurate or precise, you would say that the first target has bad accuracy because none of them are hitting the bullseye. Plus, if you average where the shots are landing, they're sort of up and to the left of where they're supposed to be, and they're bad precision because they're not close to each other. The next target actually has pretty good accuracy on average, because one shot is a little high, one shot's a little low, one shot's a little to the left, one shot's a little to the right. So on average, they're pretty much hitting the center. But they have bad precision because they're not close to each other. The third target is the best target to explain accuracy and precision to students. Bad accuracy would be described because they're obviously not hitting the bullseye, but they're good precision shots because they're close to each other. And the last one is, of course, good accuracy and good precision because they're obviously close to each other and they're obviously in the bullseye. So good accuracy is on target and good precision is close to each other. The next thing we talk about is significant figures, and this is a confusing topic for chemistry students because in math class you don't worry about significant figures, because typically in math class you're not doing anything about measurements. You're just talking about pure numbers themselves. But in chemistry, we have to discuss the concept of significant figures because they're used to determine how precise a measurement is. So they're used to determine the precision of a measurement. So a good example would be a scale. If you're stepping on a bathroom scale, let's say, and it reads 135 pounds, that has a different amount of precision than a scale that might read 135.13 pounds. Well, what's the difference between one scale and another? Well, it's their precision, or the total number of significant figures in a measurement. So a significant figure tells you how precise your measurement is. So the 135.13 pounds is more specific, more of a precise answer to how much you weigh compared to just 135 pounds. Now, when you're taking a measurement in a chemistry class or a science class, you're supposed to record the measurement with the correct number of significant figures. So here's the rule. You have to record all the numbers of the measurement that you know for sure, and then the last digit in your measurement has to be estimated, which basically means you're going to read in between the marks that are on, let's say, a ruler or on a balance, or if you have an electronic balance and you might have a number on that balance flickering between, let's say, a 4 and a 5, then back to a 4, then a 5, then a 4, then a 5, then a 3, then a 4, then a 5, then a 4, or whatever. You get my point. You're going to have to basically estimate that last digit on that balance. You're going to have to make it either a 3, 4, or 5, and it doesn't really matter in terms of how many figures you're going to have in your final answer, but you do have to estimate that last one. So let's look at some examples. Here is an object placed on a ruler. It's measured in centimeters. We definitely know it's 11 centimeters, and we definitely know it's at least 11.6 centimeters, but that last digit we have to estimate. So we're going to say it's, let's say, 11.65 centimeters. The 5 is our last significant figure because that was estimated, where we read in between the 0.6 mark on the ruler and the 0.7 mark on the ruler. Now it doesn't really matter if you said that it was 11.64 centimeters. You still have those 2 decimal places appearing in your final answer for a grand total of 4 digits or 4 significant figures. The next ruler doesn't have as many tick marks on it, so you have to estimate between 50 and 60 centimeters. So you definitely know it's 50 something, and we said in class that it's around 58. And again, you could have said 59 or you could have said 57. You still would only have 2 significant figures. So the top ruler that can go to a couple decimal places is more precise than the second ruler because the first ruler has more significant digits. It has a total of 4 sig figs, where the second ruler only has 2 sig figs. And of course, sig figs is abbreviated for significant figures. Now, if somebody else has already recorded a measurement and you're just reading their measurement, you should be able to count how many significant figures they have recorded in their measurements. And here are the rules to count somebody else's sig figs in a measurement that has been given to you. The first rule is called the non-zero rule, and these are all just my nicknames for the rules. They're not necessarily from your textbook, but it simply states that if the number is a 1, 2, 3, 4, 5, 6, 7, 8, or 9, it automatically is either known for sure or it was an estimated digit. So it counted towards the precision of a measurement. So if you had a scale that read 2.35 grams, it would have a grand total of 3 sig figs. If you had a scale that only read 2,200 grams, you would have to assume that it only had 2 significant figures in that measurement. So maybe it can only measure to the nearest 100 grams. So it's either 2,200 grams or 2,300 grams or 2,100 grams. But they definitely knew it was in the 2000s, and they must have estimated that last hundreds place position. So this would only have 2 significant figures. Now the remaining rules deal with zeros. The straddle rule is my nickname for any zero that has been straddled by 2 significant figures. So if a zero is in between 2 sig figs, it itself must have been known for sure. So the 2 was known for sure, the 0 was known for sure, and they're estimating the length to the nearest meter. So it's 205 meters. So that has a total of 3 sig figs. Now it doesn't matter if there's 1 0 in between or 2 zeros in between non-zero digits, it still would be a sig fig. So in the next example, there's a grand total of 4. And in the last example, both of the zeros that are straddled by the 7s count towards the precision, but the last 2 zeros do not, because they're not in between 2 sig figs. They're just at the end of the number. So that has 5 sig figs. The next rule I nicknamed the righty-righty rule because a 0 that's to the right of a decimal and anywhere to the right of a significant figure must count towards the precision. So again, it must have been either known for sure or it must have been the last digit that was estimated. So for example, if you have a stopwatch and you stop the watch and the watch reads 2.30 seconds, that would contain 3 significant figures because the 0 at the end of the number is after the decimal point, which is the first stipulation for the righty-righty rule, and it's to the right of the number 3. So it's to the right of the decimal and to the right of a sig fig. So I basically tell the students, zeros at the beginning of a number, they don't count, but zeros at the end, as long as they're after a decimal point, do count towards the precision. If you had that same stopwatch and you actually stopped it at exactly 20.0 seconds, all of those zeros would be significant, and here's why. The 2 obviously counts as a sig fig, and the 0 that's after a decimal point is also to the right of the 2, so it counts as a sig fig, which means the 0 in the middle would be a straddle rule 0. So that's a significant figure. So again, as long as zeros are after a decimal at the end of a number, they count. And in the last example, we see 0.00, 3060. Well, which zeros count towards the precision? The beginning zeros don't count because they're not a righty-righty 0. I agree that some of them are to the right of a decimal, but they're not at the end of the number, they're at the beginning of the number, so they don't count. Only the 3, the 0 in the middle, the 6, and the 0 after the decimal at the end of the number would count towards the precision. So again, it's zeros that are to the right of a decimal and at the end of the number that count towards the precision. So what does this mean? If you measure something that was 0.003060 kilometers long, you would definitely know the 3 for sure, the 0 for sure, the 6 for sure, but you're estimating that last 0. Maybe it landed right on the mark on your ruler, or maybe it's an odometer or something and that last little digit clicked over to a 0. That was your estimated 0. So if you go back to the to the rulers that we had in the previous examples. One ruler read 11.65 centimeters long. Well, what happens if it was 11.6 right on that line? Well, then you could call it 11.60. That last 0 is your estimated digit, and so it would still count towards the precision. On the next page we have two other rules. The bar rule is what we use to tell people that a 0 before a decimal point was the last estimated digit. So if you had 3 million meters per second as a velocity and you wanted to tell people that you rounded it off to the nearest 1,000 of meters per second, you could put a bar or a line over that 0 where you're telling people, okay, that was my estimated digit. So 3 million with a bar over the third 0 would contain a total of 4 sig figs. Let's say you had a scale that read to the nearest pound, and you put some object on the scale and it read exactly 20 pounds. Not 21 pounds, not 19 pounds, exactly 20 pounds. Well, if you want to tell people that you rounded to the nearest pound, you'd have to put a bar or a little line over that 0 to tell them that's your last sig fig. So that only has 2 sig figs. Now the last rule is when you count an object. If you physically are counting the number of objects, such as 15 students walk into a classroom, you know that number of students exactly. You're not estimating a crowd of students, you're actually physically counting the number of students that walk through the door. Well, you know the precision of that measurement to an infinite amount of sig figs. It would be the equivalent of saying there's exactly 15.000000000 students, and the zeros go on forever. All of those zeros would be considered righty-righty rule zeros, so they would be significant, but they're kind of unnecessary because you've physically counted the 15 students. If you had 29 pencils in a container and you physically counted the 29 pencils, you're not really measuring the pencils, you're just counting them. That would contain, again, an infinite amount of precision. And if you have a conversion factor that's known absolutely for sure, like there's 7 days in a week, then that is, again, you're just counting the number of days in a week. There's always 60 seconds in a minute, so that would again be known to an infinite amount of precision. It's absolutely known 100% sure that it's 60 seconds in a minute. It's not like you're timing an object or something like that where you're measuring it with a stopwatch. There's always 60 seconds in a minute because it's a conversion factor, so that's known to an infinite amount of precision. The next lesson that we do is scientific notation. And scientific notation is a way of representing really large numbers or really small numbers using a power of 10. It basically will eliminate all of these insignificant zeros that we just discussed in the previous lesson. So if you have a number that's shown on the screen, I think that's 5,203,000,000,000 miles. Well, the only digits that count towards the precision would be the 5, the 2, the 0, and the 3. And so you can actually write this number using a power of 10. It happens to be 10 to the 12th, and that eliminates all these insignificant zeros. If you have another value shown on the screen as 0.000000042 millimeters, you only need to worry about the sig figs, which is the 4 and the 2, and then you can write all those zeros as some power of 10. It happens to be 10 to the negative 8th millimeters. So now I'll teach you how to get the positive powers of 10 or the negative powers of 10. Basically, all you need to do is write down the sig figs. You need to put the decimal point between the first and the second sig fig if there is a second significant figure. If there isn't a second significant figure, you don't need to worry about a decimal point. Anyway, then you write down times 10 on your piece of paper or whatever you're writing on. If you have a calculator, sometimes when you hit the exponent key, you'll get a little E to show up on the screen, and I discussed that in class, the way a calculator writes numbers in scientific notation, but for us we'll just write the little times 10 sign. And then you need to count how many places the decimal has moved. It originally had a location, now you're putting it between the first and second sig fig, so you have to count how many times you move the decimal point. Now if you moved it and the original number was greater than 1, as in a really big number, then you're going to have a positive exponent, and if your number was smaller than 1, it's going to be a negative exponent. So again, big numbers have positive exponents, and really dinky numbers like the 0.000000042 or whatever it was has a negative exponent. So we're going to do some practice problems on the next page. Here you have 477 million miles. Since this number is greater than 1, we know it's going to be a positive exponent. We have to write down the sig figs, which is the 477. The decimal goes between the 4 and the 7, and then if you count how many times the decimal point has moved from its original location to its present location, it's 8 times. So you basically are going to be taking the number 4.77 and you're going to multiply it by 10 8 times, and you'll end up with 477 million miles. In the next example, we have 0.000910. The 9, the 1, and the last 0 are your sig figs. You put the decimal in between the 9 and the 1, and then you count how many times the decimal has moved. It happens to be 4 places. Since your original number is really small, it's going to be a negative exponent. Now here's the cool thing about negative exponents. If you count how many zeros are before the 9, it happens to be your exponent. So there's 4 zeros at the beginning, it's a negative 4 exponent. That only works for negative exponents, it doesn't work for positive exponents. In your next example, you have 6.30 times 10 to the 9th miles, and you have to write it in the expanded form. So we're going to take our decimal point and we're going to move it to the right a total of 9 times. And so you end up getting this value of 6,300,000,000. So a 10 to the 9th power always represents a billion. 10 to the 6th would represent a million. So anyway, there's one other thing that we have to do. There was a 0 in the scientific notation that was a sig fig, and we have to keep that as a sig fig, so we have to put a bar over it in order to keep it as a sig fig. So when you change from scientific notation to the expanded regular form, you can't lose sig figs. In the last example, we have a negative 6 exponent, so we know that there's going to be 6 zeros at the beginning. And then you'll have the 388 at the end of the number. So we've moved the decimal point 6 places to the left this time. The next thing that we do is how to round off calculations when you're concerned about the number of sig figs in your final answer. So there's 2 rules. When you add or subtract, there's a rule, and when you multiply or divide measurements, there's a rule. And so all the answers are rounded off when you add or subtract measurements to the least number of decimal places. So in the example, we have a measurement with 3 decimal places, the middle measurement of 0.33 only has 2 decimal places, and the last measurement has the most precision of 4 decimal places. But the rule tells us that we can only keep the least number of decimal places, which was 2. So we can round the 0.16 to 0.17 and keep those 2 decimal places, and that would limit our precision in our final answer. Now when you multiply or divide measurements, all the answers are going to be rounded off to the least number of significant figures found in your original measurements. So we'll look at an example of that in a little bit. So let's do the 3 practice problems. So here we have some centimeter lengths that are going to be added and subtracted from each other. The first measurement has 2 decimal places, the next measurement has 3 decimal places, and 2.1 only has 1 decimal place, and that limits our final answer. So we can only keep 1 decimal place in our final answer, so the 4.739 has to round off to 4.7. You can only keep that 1 decimal place. In the next measurement, since they're multiplied together, we're going to keep the least number of sig figs, which happens to be 2. There's 2 sig figs in the measurement 2.7 meters, so when you multiply this length and width together, you end up getting an area that's rounded off only to 2 sig figs of 98 square meters. In the last measurements, it's a density. We're going to divide a mass by a volume. The mass has 2 sig figs. The volume has 3 sig figs, so we're limited in our final answer to only 2 significant figures. So you're going to round it off to 5.9. The 8 actually rounds up to a 5.9. And that's how you round off using sig figs. And I'm going to stop the lecture here because we're going to have a quiz over part 1, and then we'll have a quiz over density of the metric system, and the next slide is density. So we're going to stop this lecture at this slide.